paper that's the bond connection, joined with Benny Moldovanu and Philip Strack. It's called Majorization Extreme Points with Economic Applications. And kind of the starting point for the paper was that we discussed our recent work, what we've been working on, what we've been reading, and we realized that many of the topics somehow seemed connected, but we couldn't figure out what precisely was the connection. So we started to look into that. So in a sense, we could say one of the first questions that we really were interested in studying is what were the connection between the problems that we've been thinking about. These problems involve, for example, auction design that Benny and Philip have been working on. So we've been reading about information design, about optimal delegation. We realized there might be some connection to general decision under uncertainty. So one question is, what is the connection between all these topics? This was our first question. So one possible answer to this question and the perspective that we take in this paper is that in all these problems, you could formulate it as a problem where a principal wants to maximize her payoff by choosing a function, but this person is constrained by, he can only choose a monotone function and a subject that is a function that's subject to some majorization constraint. And I'll explain in 2 slides what we mean by the majorization constraint. So what we found interesting initially is that somehow these constraints come for different reasons. So some of the problems that I mentioned here, like auction design or optimal delegation, are problems of mechanism design where you have a privately informed agent. And incentive compatibility requires that the principal chooses a monotone function. In some of the other applications, like information design, it's really someone chooses a random variable, and this is often modeled as you're choosing the CDF, the cumulative distribution function of this random variable, and this induces the monotonicity constraint because the CDF is non-decreasing. And similarly for the majorization constraint, so you'll see later that in auction design, this majorization constraint stems from a physical feasibility constraint that stems from the number of objects that are up for sale. In information design, for example, this stems from, usually we're interested in having mean preserving spreads or mean preserving contractions. We'll see that in optimal delegation, this majorization constraint stems from, in a sense, the variance being a non-negative number. So in all these problems, you have the same type of constraints, but for different economic reasons. So this is our first answer. So what's the connection between these problems? This would be one possible answer. And if you take this perspective, it might guide you the way in what kind of tools would be useful to study these problems, to have a unified perspective or unified tools for all these problems that are usually or often studied with very ad hoc methods, so different methods for different problems. Kind of this guided what we wanted to do, and from a methodological perspective, the main results that we get in this project are a characterization of the extreme points of 2 sets. One is the set of all those non-decreasing functions that are majorized by a given function, and a separate set that we're looking at is all those non-decreasing functions that majorize a given function. So the first step is providing a characterization of the extreme points, and then we look into what are some tools that one can use to solve optimization problems where these sets exactly form the constraint set, the feasible set. And then finally, the economic applications, we show that a number of economic problems, especially design problems, like information design, mechanism design, can be formulated in this way, and you could use the tools that we have to obtain a number of results. Some of them are known, which just give different proof, and some of the insights might be new. So some applications of our approach, it would be characterizing which persuasion mechanisms could be optimal, which delegation mechanisms could be optimal, or a version of border theorem. So these are some of the applications that I plan to go over later. So if there are no questions, I'd like to start by giving you explaining more detail what I mean by majorization, because this was very vague so far. So majorization is a tool that has been developed by Hardy, Littlewood, and Polya. It's mainly has been applied to Euclidean vectors, and it has proven a useful tool in a number of mathematical areas, maybe most famously provides a unified tool to study inequalities. Has been proven very useful there. Majorization has also been used to provide an order on functions, and what we're going to do is use it for functions. So throughout this talk, we will always be talking about non-decreasing functions that are defined on the unit interval. And then we say that the function f majorizes the function g, denoted by this curly inequality, if for every x we have that the integral of g from x up to 1 is less than the integral of f from x up to 1, and equality holds if we evaluate this for x equal to 0. We also say that f weakly majorizes g if these inequality hold, but we do not require equality at 0. So majorization now here is defined for non-decreasing functions. It sometimes is extended to a relation between arbitrary and non-monotonic functions. Then you require these inequalities for the non-decreasing rearrangements. So first you rearrange the function to make it non-decreasing, and then you check whether these integrals satisfy the inequalities. So an example would be here the functions f and g, both are non-decreasing. And we have that for every point, if you compute the integral from this point up to 1, the integral of the function f, the blue function, will be greater than the integral of the red function g, and equality holds at 0. So especially with this picture, you will recognize that, if these were the cumulative distribution functions, this would be exactly that the corresponding random variables would be mean preserving spreads of each other. Okay, so this explains already why this order plays a role, for example, in information design. We stick to the notation of majorization to connect to some of the mathematical literature, and also sometimes it's more reasonable to think of these functions potentially as densities, for example, and that then it would correspond to first order stochastic dominance. So throughout, whenever we talk about majorization, we mean this collection of inequalities are satisfied, and equality for 0. Okay. So our first aim is now to characterize the extreme point of two sets. So now fix some non-decreasing function f, and then we are interested in all those non-decreasing functions g that are majorized by f. This is one of the sets that we're interested in. Another set that we're interested in is all those functions g that majorize f. Without the monotonicity constraint, these sets have received some attention in the mathematical literature, notably by Riff. And one of his most important results is a characterization of the extreme points of all those functions that are majorized by a given function. So what we do instead is we look at the subset of those functions, namely only at the non-decreasing functions. So this will give very different extreme points. But since this was one of his most useful results, our starting point is also the aim to provide, to characterize the extreme points of these sets. And just to remind you, this monotonicity constraint that imposed, it's really our motivation, our economic application. It turns out that for many economic applications, this monotonicity constraint is relevant. So it should be interesting to characterize the extreme points. So as a quick reminder, an extreme point of a convex set is an element of that set that cannot be written as a convex combination of two distinct elements. So for example, for this polytope here, the set A, the dots correspond to the extreme points. So before we go into how the extreme points look like, why is it interesting to look at these extreme points? Well, for our applications, there are two main reasons why knowing a lot about the extreme points is useful. The first stems from Bauer's maximum principle, which essentially says that whenever you maximize a continuous and convex functional on a compact convex set, then a maximum will be attained at an extreme point. But in economics, we're often interested in maximizing convex or linear functions. And therefore, if you know a lot about extreme points, you know a lot about the solution to the corresponding maximization problem. and maybe even independently of what exactly is the specific functional form that you want to maximize. And moreover, knowing the extreme points, it could help you to solve the optimization problem, because now you don't have to search over all the set. You could simply optimize over the extreme points. So this is one motivation why it's interesting to know a lot about extreme points. The second reason stems from results like Kara-Theodori theorem or the Krein-Milman theorem, which, for example, says that any compact and convex set is the closed convex hull of its extreme points. So again, give you a simple picture, like here in finite dimension, this is just saying that every element of the set can be written as a convex combination of the extreme points. Why is that useful? Well, sometimes you know that all the extreme points share a certain property. And now if you know that this property is preserved under taking convex combinations, then you can immediately deduce that this property holds for all the set. So for example, in this picture here, each extreme point has each dimension non-negative. So each extreme point lies in the positive orthant. So clearly this is a property that's preserved under taking convex combinations. So then you can deduce that the set A lies in the positive orthant. Of course, that's kind of a trivial example where you don't need it, but sometimes you have a more complicated convex set, and you might have a more complicated property where it's too hard to check whether this is satisfied for every element of the set. But with enough structure on the extreme points, it might be possible that you can exactly say that this property holds at least for all the extreme points. And then if you then also know that this property is preserved under taking convex combinations, then you can deduce that this property holds. So this will be the second reason why it's useful for some of our applications to know how the extreme points look like. Okay, so this is kind of the motivation for why we're looking at the extreme points of these sets. And then my plan for the presentation now is to give you first some theoretical results, the characterization of the extreme points. And then, so that it doesn't get too boring, to provide you one applications of how you could use this result to auctions. Then I'll give some more theoretical results and then some more applications. So if I would be only going over the theoretical results, that might be too boring for a talk. And on the other hand, if you include lots of applications, it might be hard to follow all the applications, because there's not too much time to explain all of the assumptions. So, but these are all fairly standard economic models. So hopefully you've seen them before and you're able to follow through the applications. And if you have any questions, please interrupt me. Okay. So are there any questions so far about what we plan to do? So now I introduce some notation. So the two sets that I've mentioned before that we're interested, these are what we call the monotone orbit and the monotone anti-orbit. So we denote by omega of f, what we call the monotone orbit of f. These are all those non-decreasing functions that are majorized by the function f. And by the monotone anti-orbit, we denote by phi of f. These are all those functions, all non-decreasing functions g, that themselves majorize the function f, and an additional property which essentially ensures that g and f have the same range. So this condition, first on a technical level, it ensures that this is a compact set, as we will see next, so which ensures that we have extreme points and optimization problems that we are interested in have a solution. And it turns out that this assumption is a relevant assumption in the economic applications. So from an economic standpoint, really we're interested in this set with this additional condition that G and F have the same range. So now that we're working in function spaces, it's no longer true necessarily that you can write every element of this orbit, for example, as a convex combination of the extreme points, because in a sense you might need infinitely many elements to write G as a convex combination of infinitely many extreme points, and convex combinations are only defined for finitely many elements. So there's a nice extension of the theory due to Choquet, which in a sense replaces convex combinations by suitable integrals. So our first technical result is just that these sets that we're interested in, the orbit and the anti-orbits, are convex. This is easy to see, and they're compact in the strong topology. This follows because these are just monotone functions. So these are functions of bounded variations. Moreover, they are uniformly bounded. So Heller's selection theorem implies that these are compact sets in a norm topology. And this then in turn allows us to use Choquet's result, which tells us that for every element G in the orbit of F, you can find the probability measure lambda G that's supported only on the extreme points of this orbit, and such that G equals the integral with this respect to this probability measure lambda G that's supported only on the extreme points. Okay, so this is a suitable generalization of taking convex combinations. Now you might need infinitely many. So you do this by having this integral. It's an integral in the Bochner sense. Because like if this were a convex combination, this would be all be vectors, and I take convex combination of vectors. Now I take an integral of these vectors. So it's a vector valued integral, so it's a Bochner integral. But in a sense, if you don't want to bother with this, you can simply think of this as a generalization of convex combinations. And we have a similar result for the anti-orbit. You can also use Choquet's theorem there. So with this in hand, now let's look at the extreme points. So in function spaces, sometimes it's the case that all these nice results are not that useful simply because there are too many extreme points and there's not enough structure on the set of extreme points. So you can't do much with it. So it turns out that we are lucky. These sets, these have very nice extreme points that have a lot of structure. So on this slide, I'll give you the first result, which is a characterization of the extreme points of an orbit. And then I'll show you in a few slides an application of this result. So the first result is that the function G is an extreme point of the orbit of F, if and only if there's this countable collection of intervals, such that outside of these intervals, the two functions G and F coincide. And on each of the intervals, the function G is constant, and its function value equals the average value of F on this interval. Okay, how does it look like in a figure? So the dashed line is the function F. Now the function G is an extreme point of the orbit of F. Why? Well, first it's an element of the orbit because it's a non-decreasing function, and you can check that the majorization constraint is satisfied. So whenever you compute the integral from some point up to 1 of G, you will get a smaller value than the corresponding integral for F. And you have equality here. Now this is an extreme point because we have one interval. On this interval, the function G is constant, and the function value of G equals the average value of F on this interval. And outside of this interval, the two functions are equal to each other. Okay, so the extreme points have a very nice structure. They could look more complicated than G, but all you need to know is really just this collection of intervals. And then you know the function will be constant on these intervals and it will equal F outside of it. Okay, is it clear what the result is saying? Then I'll give you the quick idea of the proof. So the easier direction is to show that the function like this G is an extreme point. So if the function takes this particular form, then it will be an extreme point. And essentially, really, the idea is that at each point of the domain, either the monotonicity constraint or the majorization constraint will be binding. So for example, if you pick an arbitrary point here, now if you compute the integral from this point up to 1, well, the integral of F and the integral of G will be the same. So this means the majorization constraint is binding. The only points where it's not binding are in this interval, but then on this interval, the function G is flat, so the monotonicity constraint will be binding. And essentially, this shows you that you cannot write this G as a convex combination of two elements of the orbit of F. Because if you were able to do this, well, here the majorization constraint is binding at every point up here. So you know, if you write G as a convex combination of two functions, well, for both of these functions, the majorization constraint here must be binding as well. But then it must be equal to F. And similarly here on the flat part, well, if you want to write G as a convex combination of two non-decreasing functions, these two functions have to be flat here as well. And since here the majorization constraint again will be binding, this pins down that you cannot write G as a convex combination of two distinct elements. For the other direction, we have to show that every extreme point takes a form like this, that you only have these intervals, and outside of the intervals, G and F coincide. And kind of the main step to show is that if, suppose G, it's without loss to assume that it's a right continuous function. So suppose that G is strictly increasing at the point, like for example here. Now, if the majorization constraint were slack, that would allow you really to write G as a convex combination of two distinct functions that both are in the orbit of F, like for example, these two functions. So if the majorization constraint were slack at this point, it would be slack on an interval around this point. So you could pick 2 points where the majorization constraint is slack, and then write G as a convex combination of G plus U and G minus U, for example, these two functions. So then G wouldn't be an extreme point. So it must be that whenever G is strictly increasing, then the majorization constraint must be binding. So this means that the function f and g, either they coincide whenever g is strictly increasing, or the function g is flat. This is the argument why the extreme points have this particular form that I showed you here. So either the two functions coincide, or you have these intervals where the function g is flat. So is it clear what the result is saying and what's the rough idea for the proof? So these are the extreme points. It's not so hard to show, or it's fairly easy to show that these are also exposed points. So this means each of these extreme points uniquely maximizes some linear function. So before I give you an application of this result, I'll show you the corresponding result for the second type of sets, for the anti-orbits. So suppose here that the function f is not only non-decreasing, but it's also a continuous function. Then G is an extreme point of the anti-orbit of F, if and only if you can find a collection of intervals, again, a countable collection of intervals, and potentially some sub-intervals of these intervals, such that the following holds. Again, outside of this collection of intervals, the function G equals the function F. Now, on each of these intervals, from x lower bar to x upper bar, we have that the function g takes the value f of x lower bar on the first part of the interval, takes the value f of x upper bar on the last part of this interval, and it might take some value vi in between. So what does it mean? It's maybe easier to see it in the figure. So again, here now g is an extreme point of the anti-orbit of f. We have one interval from x lower bar to x upper bar, and outside this interval, the functions g and f coincide. And on this interval, the function g exactly takes two function values. It's equal to f of x lower bar on the left part and f of x upper bar at the right part, such that again, on average, the function g and f have the same value on this interval. So this is if this interval, the subinterval y lower bar to y upper bar is empty, then the function g takes only two values on this interval. And the only other possibility for an extreme point is that the function g takes three values on this interval. Like here, where you have a non-degenerate interval y lower bar to y upper bar, where the function takes some value b, such that again, on average, the function value of g equals the function value of f. Okay, so these are two different kind of extreme points, and we will see later in the economic applications that economically they have quite different properties in some of our applications. So the proof method is fairly similar to the one before. It's maybe slightly more work because now you have these two different kinds of extreme points. But the main takeaway so far is, so we have these sets that are defined by a monotonicity constraint and the majorization constraint, and we characterize the extreme points, and these extreme points take this fairly simple form. They are all characterized by these intervals, where either the function g will be constant, or it will take 2 or 3 values for the case of the anti-orbit. So instead of going deeper in the theory part, if there are no questions, then I'll move to an applications to show how these results could be used. So the first application is to a very standard auction model. So the symmetric auction with independent private values. So suppose now we're in a world there are n agents. Each agent is characterized by a one-dimensional type. Let's say it's drawn from the unit interval according to a distribution with a bounded density. And then you have an auctioneer who's going to sell objects of various qualities. So it's without loss here to assume that there are n objects that you're going to sell, and the qualities are ranked. Quality Q1 is the object of the lowest quality, and it goes up to the Qn object with the highest quality. Each agent is interested in buying at most one object, and if an agent with type theta I obtains an object of quality Qm, then his utility will be theta I times Qm minus the transfers. So this is a fairly standard auction model with one-dimensional types. The only difference is now that you have multiple heterogeneous objects, but they're not that heterogeneous. It's really, they differ only in the quality, and all the agents value have the same audit ranking over the qualities, so that we still can characterize the buyers by one-dimensional types. So this is the physical setup. Now, what does the auctioneer do? The auctioneer is going to decide on an allocation, and an allocation could potentially be stochastic. So we let this capital pi denote the set of doubly substochastic n times n matrices. So these are the matrices that have row and column sums less than 1, and all entries are non-negative. And then an allocation rule is simply a mapping that sends the reported types of the agents into such a stochastic allocation. And the interpretation is that if the entry of this matrix in row I and column J is the probability that agent I obtains an object of quality Qj. Okay, so alpha ij is a function of all the reports of all the agents, and it's the probability that agent I gets object J. So one particular allocation rule would be a very simple one. You take the object with the best object, the highest quality object, and you give it to the bidder with the highest type, and the second best object to the agent with the second highest type, and so on. So this is the assortative allocation rule. And we break ties, let's say, by fair randomization. And this assortative allocation rule will play a special role soon. Now, one common trick in this auction design problems is that sometimes actually it might be easier not to optimize over these allocation rules directly, because these are functions from a high dimensional space, because they're functions on n-dimensional space if there are n bidders. And you're picking a matrix for each such report. So it turns out that sometimes it's easier to work with the interim allocation rules. So in this setting, we define the interim allocation rule as follows. So phi I of theta I, so this is agent I's interim allocation rule. Given his reported theta I, this is the expected quality that he obtains, taking expectation over the randomization in the mechanism and taking expectations over the distribution of other agents' reports. Okay, so alpha I is a vector which has for each possible quality the probability that the agent I gets this object, and we take the dot product with the vector of qualities. So now for a particular profile of reports, this would be the expected quality that the agent gets. And then we also take expectation over the reports of other agents. So these interim allocation rules are easier to work with because now this is a function, a one-dimensional function. It depends only on agent I's reports. And to simplify notation even more a little bit, we could also express this as an interim quantile allocation rule, but instead of writing this as a function of the type, we could write this as a function of the quantile of agent I's type, this transformation. Now, a very classical question in this auction design literature is, which interim allocation rules can you actually implement? Right, for example, I could promise all relatively high agents of all relatively high types of all agents that they get the good object with a very high probability. That would be an interim allocation rule, but it turns out that there's no way you could physically implement such an interim allocation rule because you cannot give the good object to more than one agent. So the classical question is, which interim allocation rules can actually be implemented via some ex post auction, some allocation rule? And it turns out that you can formulate this feasible set as a set characterized by a majorization constraint and a monotonicity constraint. So the result here is that a symmetric and monotone interim allocation rule phi is feasible if and only if its corresponding quantile allocation rule psi is weakly majorized by the corresponding rule that you get from assortative matching. So assortative means highest object to highest type and so on. So this is exactly now the set of feasible quantile allocation rules is characterized by a monotonicity constraint and by a weak majorization constraint. So it looks maybe slightly unusual here. It becomes more concrete if you reformulate this, for example, for a setting where you have just one object for sale. If you have one object, you can rewrite this condition as the following: n times the integral of phi with respect to the CDF is less than 1 minus f to the power n. So what does this say? Well, the integral from t up to 1 of phi is essentially the probability that a given agent has a type above t and obtains the object. So we multiply this by n, and then this gives us the probability that there is some agent who has a type that is higher than t, and this agent obtains the object. That's the left-hand side. What is the right-hand side? Well, this is simply the probability that there is some agent who has a type above t. So it's clear that this is a necessary condition because you can only, I mean, this is logically, this is, there is an agent above t and he gets an object, and there is some agent with type above t. So it's clear that this condition is necessary. If this phi is a feasible interim allocation rule, then this inequality must hold. And it has been conjectured, I think, by Matthews and Maskin and Riley that this condition is also sufficient. And this is indeed what Kim Border showed. Such an interim allocation rule is feasible if and only if these inequalities are satisfied for all t. There are many generalizations and proof now. So here we have a formalization in terms of a majorization constraint. And here it's extended to having multiple objects of differing quality. So this is an example how you could use our results to prove this result. So we've seen, so the argument is fairly simple to show that this condition is necessary for an interim allocation rule to be feasible. So the harder direction is to show that this is a sufficient condition. Well, let's look at the extreme points of this set. So from our previous result, we essentially know that the extreme points will be functions like this psi here. Either they coincide with psi star, or they will be constant on some intervals. Well, if psi was equal to psi star, this would be one particular extreme point. It's easy to implement this function because we know this corresponds to the assortative matching rule. So you can implement psi star just by giving the best object to the highest agent and so on. Now, the only other thing that could happen at an extreme point is that you have these flat parts. And it's also fairly easy to implement this, right? Because all you have to do is to randomly redraw the agents from this interval to ensure that they all have the same expected allocation rule. So this shows that every extreme point of this set can actually be implemented via some physical allocation rule. And this shows that every extreme point of this set at least is feasible. It also is easy to see that this property of being feasible is preserved when taking convex combinations, because if you have some interim allocation rule and you know you can implement it via some physical allocation rule, and you have another interim rule that you can implement, well, a convex combination of these two interim allocation rules, you can simply implement by taking the convex combination of the two corresponding physical allocation rules. So now we've shown that every extreme point of this set can be implemented via some allocation rule, and that this is a property that's preserved under taking convex combinations. So therefore, we can conclude that all this set is actually feasible. Every element of this set is feasible in the sense that you can actually implement it. So maybe a possible other, so this is a proof approach is slightly different from the usual proofs for border theorems, which are usually based on duality results, like separating hyperplane theorem, or for example, using a version of Farkas lemma, or using a min flow max cut duality result. So here essentially we get this relatively directly from the characterization of the extreme points. Another observation is that the extreme points, the way you implement them, it's actually easy to implement in dominant strategies. It's a well-known result that the assortative allocation rule can be implemented in dominant strategies. But then this randomization is also easy to implement in dominant strategies. So another conclusion is then, for example, immediately that any symmetric and Bayesian incentive compatible mechanism can be implemented, or for this there exists an equivalent dominant strategy mechanism, such that all the agents get the same interim utility and you create the same social surplus. So for one object, this is the result in Manelli and Vincent. By Gershkov and co-authors, this has been generalized to arbitrary social choice settings. So here, this is not a new result, but it's kind of fairly easy to get this as a corollary of this border theorem. So that's why we thought it's useful to include it here. So this is kind of an illustration of how you could use the characterization of extreme points, why it could be useful. And in particular, the way we use this is that we had a property of the extreme points that's fairly easy to show for the extreme points, namely that every extreme point can be implemented. And then you can deduce from that that this is actually a property of every element in this convex set. So this was one way I mentioned in the introduction, how we're going to use our characterization. And then the second way we wanted to use it is to develop some tools to solve optimization problems, where the feasible set is characterized by a monotonicity constraint and by a majorization constraint. So this is what I'm going to turn next if there are no questions. Okay, now, so the first thing is an old result, and it turns out to be very useful for the problems that we're looking at. So this majorization defined on the set of non-decreasing functions is a partial order. And you could wonder, when is a function monotone with respect to this partial order? So a functional that is monotone, increasing with respect to the majorization order, is historically called Choquet-convex. And the following result is essentially an inequality due to Fan-Lorentz, characterizes a class of functionals that are Choquet-convex. So K will be a kernel, will be a function that maps the unit square to the real numbers. And then the functional that we're interested in this result says that the value of the functional v at f is equal to the integral of this kernel evaluated at f of t and t. And this functional will be sure convex if and only if this kernel is convex in the first argument in u and supermodular in u and t. So once we started looking into various applications, we saw that this inequality could be used in many economic applications because majorization constraint or majorization order shows up in many economic applications. So it's always interesting to know when you have a monotonicity with respect to this order. So one application, for example, that we mentioned explicitly is to rank dependent utilities. This is a decision maker who not only distorts the monetary payoff via some Bernoulli utility function, but also distorts the lotteries, essentially. Goes back to Quiggin and Yari. And a classical question in this literature was, when is a decision maker with such a rank-dependent utilities risk-averse? But it turns out that this question exactly fits to this inequality, and you get an immediate answer that's usually derived via some hard work. So this Fan-Lorentz inequality is very useful to keep in mind for all kinds of economic problems. The way we are going to use it is as follows. So if these conditions are satisfied, this is very nice because then you get that the function that you're interested in is sure convex. So you know that you want to choose the largest function in the majorization order to maximize some function. Or if you're minimizing something, then you want to choose the smallest function in the majorization order that's feasible. So that's a very strong result, but of course it has very strong prerequisites. So what we are going to do is we look at a particular class of optimization problems, namely linear problems, and we're going to use this Fan-Lorentz inequality to provide some tools on how to study them. So now we're looking at, suppose you have a linear objective function. So in this setting, this means you're maximizing a functional of the form. You're taking the integral of c of x, where this is some function, times what you're choosing, h of x. So this is your objective function. And your constraint is you can only choose non-decreasing functions that are majorized by f. So it turns out that there are simple solutions to these problems if c is non-decreasing, because then all the properties of the Fan-Lorentz theorem are satisfied. So this means that the objective functional is sure convex. So what you would like to do is to choose the largest function in the constraint set according to the majorization order, but the largest function obviously is the function f itself. So then f maximizes this problem. On the other hand, if this function c is non-increasing, then it turns out that this is a sure concave functional. So to maximize this objective function, you want to choose the smallest function in the majorization order. And this is the function that's just overall constant and has the same value as f on average. So the Fan-Lorentz theorem gives you simple solutions if this function c is monotone. If the function c is not monotonic, but it turns out that other extreme points other than these two can be optimal. And it turns out that these linear optimization problems where you're maximizing over the orbit have a simple solution, because essentially you can apply a version of Meyerson's ironing procedure to these problems. Even so, now you have a more complicated constraint set. Still the same tools that Meyerson used can be used using an ironing procedure to find the optimal for this problem. So it turns out that many economic problems, you're interested in maximizing a linear functional subject to the constraint that you're choosing from the orbit of a given function. So obviously auctions are one example. Procurement, I mean, it's closely related to auctions, but historically have been often analyzed using very different tools, using linear programming duality, but it turns out they have the same form, so it's easy to solve them this way. Contests are another example. some information design problems also take this form. So there are a number of economic design problems that have this form. So maybe it might help you now taking this little bit more abstract perspective to see that you can solve them all with the same tools and translate results from one to the other. So this is the first type of optimization problems that we're interested in. The second type is simply replacing the orbit by the anti-orbit. Now you're maximizing again a linear objective functional, and you can choose any function that lies in the anti-orbit of a given function f. So again, if this function c is monotone, you can use the Fan-Lorentz theorem to obtain simple solutions. Namely, if c is non-increasing, again, now this will be a sure concave problem as before. So this means you want to choose the smallest function that's feasible in the majorization order. And well, the smallest function in the anti-orbit is just the function f itself. On the other hand, now if c is non-decreasing, it's a sure convex function. So you would like to choose the largest function in the anti-orbit. According to this majorization order, the largest function is a step function that just takes 2 values. And of course, on average, it has to equal the function f. So this is the largest function in majorization order. So this will be optimal whenever c is non-decreasing. And now again, if you have a non-monotone c, it turns out that other extreme points can be optimal. So the difference to the previous problem is now that there is no simple ironing procedure that gives you the result. So here you have to work harder. You can, for a given extreme point, you could use tools from linear programming to characterize when this particular extreme point is optimal. But it turns out that this problem is harder to solve. But still, now that you know what are the extreme points, I mean, one could show when or characterize when a particular extreme point is optimal. So in the remaining time, I would like to give you 2 problems, 2 economic applications, where in a sense you can write the optimization problem for the principle as a problem of this form. So the first one is an application to information design or Bayesian persuasion, and it's a model that's been introduced by Keliner and Keliner. So you have a state of the world that's distributed on the unit interval according to some prior f. Now this is a model where you have in this relatively rich state space. And to make it tractable, the idea is you're interested only in the posterior mean. So the sender is going to commit to a signal pi. This is a signal realization space S and a family of distributions over S that depend on the realized state of the world. And then you could think of a receiver who's going to observe the signal realization, update his belief. And so given the signal, a realization S will induce a posterior Fs, which has some mean X. So whenever you choose a signal, this induces essentially a distribution over posteriors and particular distribution over posterior means. Now the idea is that the sender's payoff only depends on the posterior mean. This is to make this problem tractable, even though you have many states of the world. So the first question is, how should you write this as an optimization problem? It turns out that instead of optimizing directly over the signals, it's easier to optimize directly over the distribution of the posterior means. And this is mainly due because there's a nice characterization of which posterior means you could induce. So the result, I think, mainly goes back maybe to Blackwell, recently been generalized to these richer state spaces. So a signal there is a signal that induces a given distribution of posterior means G pi, if and only if the prior is a mean preserving spread of this distribution G. Okay, so instead now of optimizing over signals, we can write this as the sender is simply just choosing a distribution of posterior means such that F is a mean preserving spread of this distribution. So with this result, it's easy then to write the sender's problem. Well, you're going to maximize the payoff. It's a function V of the posterior mean X, and you're choosing the distribution of the posterior means G of X. And well, what are the constraints? Well, G has to be a CDF. So this means it has to be non-decreasing. And we want that F is a mean preserving spread of G. So in other words, this means that G majorizes F. So this then says that, okay, this problem of Bayesian persuasion written this way is exactly of the form we had before. You're maximizing a linear objective function, and the constraint set is the anti-orbit of a given distribution, of a given function. So now our results might potentially be useful because now you know immediately what could be optimal, because you know the optimal will be achieved at an extreme point. So what are the extreme points of the anti-orbit? Well, given some distribution F, this is the prior. The anti-orbit, the extreme point, will be functions like this G, for example. This, just to recall, so G will be equal to F, except possibly on some intervals. And on these intervals here, this function G takes two values. Now, this is a distribution of posterior means. How could you implement this? Well, whenever the state of the world lies in this interval, you could send the same signal. And then you, by observing the signal, the receiver could update his beliefs. He knows that the state of the world lies in this interval. So he updates his belief, and the posterior mean will now be a point mass at the expected value of F on this interval. And outside of this interval, you could just completely reveal the state of the world. If you do that, then exactly you induce exactly distribution of posterior means G. So such signals are in the literature usually called monotone partitional signals, because you have these interval partitions where you pool all states of the world, and outside of these intervals, you reveal the state of the world. So there's some nice results in the literature by Colotolini and Dvorak and Martini characterize when these particular extreme points are optimal, when these kind of simple signals are optimal. But already in Genskov and Kamenika, there was an example showing that sometimes stranger things can happen, namely that their optimal signal will not be, you cannot implement it using this simple interval partitions. Now, with this coming from our characterization of the extreme points, I mean, now we know what else could happen. The only other thing that could happen would be an extreme point that looks like this, where you have an interval and this function takes 3 values on this interval. So how could you implement such an extreme point? Well, this means that on this interval, you have to send two distinct signals. This would be one way to implement it, depending on what's the state of the world. Sometimes you send a signal that induces this posterior mean, sometimes this posterior mean. And again, outside of the interval, you reveal the state truthfully. So this shows that the optimal signal structure can be implemented fairly easy. I mean, you have a set of states that are perfectly revealed. Then there are some intervals where you pool all states and you always send the same signals. Now, the only other thing that could happen would be an interval of this form where you send 2 different signal realizations. So this shows exactly how strange it can get, and in a sense, the optimal posterior means will not be that strange. This is a result that you immediately get from our characterization of the extreme points. So in the context of this Bayesian persuasion setting, the same result has been obtained by Ariely and co-authors recently. So this would be now an application where knowing what the extreme points look like is interesting, because it tells you what could happen even without knowing exactly what is the payoff function precisely for the principle. So our last application will be to optimal delegation. I've seen that Anton presented recently his paper in the seminar theories. So it's not too surprising that there's also a connection to optimal delegation. So this is work that goes back, I think, to Holmstrom. And essentially, it's a mechanism design problem without transfers. So the idea is, in optimal delegation, you have two agents, a principal who can take some action, and you have an agent who has some information about the state of the world. So there's a state of world theta who's distributed according to some distribution on the unit interval. Now the agent is going to privately observe the realization of the state. And there's a set of possible actions, let's say the real numbers. Now the principal has the power to take the decision, but he doesn't know the state of the world. So the initial motivation for Holmstrom was to look at, okay, when is the principal agent to delegate the decision to the agent? And what kind of constraints would he like to impose on the choice by the agent? The idea is, okay, maybe we have some alignment of preferences. So instead of taking a decision without having any information, I simply could delegate the decision to the agent and maybe give him some restrictions on what he could choose. So what are the preferences? So here we assume that the principal and agent have quadratic Bernoulli utility functions. So if action A is chosen in state theta, the utility of the agent will be a quadratic loss function. So the agent would simply choose the action to be equal to the state. And for the principal, it's also a quadratic loss function, but they have misaligned preferences in the sense that the most preferred action for the principal is gamma of theta. So it also depends on the state of the world, but it's not necessarily the same as what the agent wants. So I use here quadratic utilities mainly because the illustration is easier, the explanation. This can be extended, for example, to the utility functions that have been used in Amador and Beckwell. So it could be done slightly more general. So this is the setting, and kind of the one idea was that instead of taking this delegation perspective as in Holmstrom, Amador and Beckwell, for example, formulated this as a mechanism design problem, and has been done earlier as well. So in this setting, a direct mechanism would be simply a mapping that maps the realized state of the world or the type of the agent to some distribution over possible outcomes. We assume here that this has finite expected value and finite variance. Okay, so there are no transfers. All you could do is you could ask the agent, what is your type? What's the realized state of the world? And commit to what's the probability distribution over the action that you're going to take. Now in the setting where you have quadratic utilities, there's to illustrate it, you can nicely rewrite it. So given some mechanism, which is a mapping from the state of the world to some probability distribution, we could represent this by the mean and the variance of the action. So mu of m is a function that maps the unit interval, so the type of the agent, to the expected value of the action that the principal takes, given this realized type. So we call this the mean action function, and sigma square m, will be the variance. So it's a mapping from, given what's the state of the world, what is the variance of the action that the principal takes. So with quadratic utilities, then you can write the agents and the principal's utility functions in this nice way, where you have a part that only depends on the mean action function, and then you subtract the variance of this mechanism, and the same for the principal. So here for illustration, it's nice to have the quadratic utilities, because now this shows you that, well, actually it's not that far from a setting where you have transfers and quasi-linear utilities. We don't have transfers, but taking this mean action is now like taking an allocation, where this is the utility function, and then the variance is essentially like making a payment. So now that it looks almost like a quasi-linear utility setting, you can apply the standard tools and, for example, try to characterize what are the incentive-compatible direct mechanisms. And the standard results, and this has been done, for example, by Kovac and Milovanov, they show that such a mechanism is incentive-compatible if and only if 3 conditions are satisfied. So the first one is the standard monotonicity constraint. This mean action function has to be non-decreasing. The second one is also standard conditions. Essentially, if these were transfers, well, we know that transfers must satisfy some envelope condition. So here also the variance must satisfy some envelope condition. And now comes an additional condition because it's not really a transfer, it's the variance. And for the variance, we need that the variance is always a non-negative number. Okay. So this is the characterization by Kovac and Milovanov. Such a mechanism is incentive compatible if and only if these 3 conditions are satisfied. The first 2 are the standard ones. The third one is the variance being non-negative. But it turns out that this characterization is still fairly hard to work with. Because think about you're going to choose such a mechanism. So this means you're choosing this mean action function. Once you choose the mean action function, essentially up to a constant, this pins down the variance that you have to assign to every possible report, because it's like a transfer. So this is pinned down, but now you also have to make sure that this variance is really a positive number. Otherwise, there's no way you could actually implement this via some lottery. So this restricts which mean action functions are actually feasible in the first place, and optimizing with this additional constraint turned out to be not that easy. So that's why it's actually useful to work a little bit more on the characterization result and think about which mean action functions can you actually implement in the sense that the variance that's required by the envelope condition is actually non-negative. So this is what we do next, and this turns out to be exactly the majorization constraint. To do this, well, it turns out that not all mechanisms can be compared in the majorization order, but every undominated mechanism can be normalized in a way that you can compare them. So we say that the mechanism is undominated if you cannot find a mechanism where the set of actions is a singleton and that yields a higher utility for the principal. Okay, so clearly from an optimization standpoint, you're only interested in undominated mechanism, no matter, for example, what the exact distribution of agents types is. So the characterization that we get, which extends the previous characterization, is the following. Such an undominated mechanism consisting of a mean action rule and the variance rule is incentive compatible if and only if you can extend it to a larger type space and normalize it in a way. So this is just a normalization, but then the substantive part is the mean action rule should lie in the anti-orbit of the identity function, and the variance must satisfy the envelope condition. So why is this, what is this about? Well, the anti-orbit, if mu lies in the anti-orbit, this means that mu is a non-decreasing function. So we know mu will be non-decreasing, and it will satisfy the envelope condition. So this essentially ensures incentive compatibility if this variance is non-negative. But it turns out that requiring that mu lies in the anti-orbit exactly ensures that the variance is non-negative. So it's an if and only if. So we get rid of this non-negativity constraint for the variance by requiring that mu lies in the anti-orbit of the identity function. And now this is a much more useful characterization, because essentially now you just have these two the standard condition, the variance is pinned down once you choose the mean action rule. And for the mean action rule, well, you have the anti-orbit as the feasible set. So this means you have the kind of the same constraints that we're usually interested in this project. And moreover, if the principal has this quadratic utility as well, then you can actually write his utility as a function that depends only on the mean action rule. The variance cancels out, and this will be a linear function of the mean action rule. So it will be the integral of some form of virtual valuation times the mean action rule. And this shows us that the principal problems now is you're going to maximize this linear functional by choosing a mean action rule, and which mean action rules are feasible, but exactly those that lie in the anti-orbit of the identity function. So again, it's the same type of problem that we've been looking at before. And what can we say, even without digging into what is the exact form of the virtual variation? Well, we know that an extreme point will be optimal if principal and agent have quadratic utilities, because it's becoming a linear optimization problem. One particular type of extreme point would be the extreme points we've seen before, where either the function mu coincides with the identity function, and then you might have intervals where the function mu takes on two values. But it turns out that these particular mechanisms are exactly the deterministic mechanisms in this setting. You could implement them by delegating to the agent, well, those actions in this interval and those actions in this interval. So what's the agent going to do is, whenever the state of the world is between here, he's choosing the action that's closest to the state of the world that's he's feasible to choose from. So these particular extreme points can be implemented as deterministic mechanisms. So we know the deterministic mechanisms can be optimal. And the only other thing that could be optimal is the other type of an extreme point, where this function takes three different values. That would correspond to a stochastic mechanism. But it also shows that actually in this linear setting, is a restricted class of stochastic mechanisms that could potentially be optimal. So this might help when solving which particular stochastic mechanism is optimal. And the tools that I've talked before might be useful to actually do that. So again, now taking this perspective of writing this as an optimization problem subject to a majorization constraint tells you that one of our standard extreme points will be optimal. So you already know a lot of what could potentially be optimal in these settings. And you can rule out many stochastic mechanisms. So Anton presented his paper here. So what we've just seen is kind of an extension of this very nice equivalence that they show between persuasion and delegation problems. So here we show that this equivalence extends to having stochastic delegation mechanisms and kind of more general persuasion mechanisms. And it provides a little bit a different perspective on where does this equivalence come from, because we've seen that in a delegation setting, the majorization constraint could be really read as coming from the variance being not exactly like transfers, because you have that the variance has to be a non-negative function. So this provides maybe a complementary perspective on their equivalence result. Okay, so to wrap up, so the idea of this project was to trying to understand connections between various economic design problems. One approach, or what we thought could be useful, is providing a characterization of the extreme points for such problems. And I've shown you a couple of examples how one could use these results for the actual applications. One clear restriction of this is everything I've shown you was for one-dimensional problems. So what we're interested in would be getting a better idea of how do the corresponding extreme points look like if you look for multivariate majorization or settings where you have multidimensional state spaces. So this is what we're working on currently. Yeah. Okay, so that's so far on my side. So let's see whether you have some questions or comments.
If there's any questions or comments, please just unmute yourself and go ahead. All right, well, it looks like you managed to give a wonderfully clear talk. it looks like there's not too many questions. I guess maybe then this is a good time to say thank you.
Thank you.